Oh, it didn't start at the beginning. Hold on, sorry. I sort of got involved with Riverwatch through the conservation district. My husband was a board member on the Mancos Conservation District for several years, and so he kind of had an in there. And I just was working with Gretchen at the Conservation District, and she's awesome. And we thought it would be a really cool thing to be able to implement it into the high school curriculum. And so we worked with them to get it started, and we started in January of last year. So I use Riverwatch as part of my high school chemistry curriculum. Last year, it was kind of just thrown in there. We didn't, I mean, they kind of got it and they got to experience it, but then COVID happened and we all went home. And so they really didn't get a full taste of what Riverwatch was. But it's basically juniors and seniors. They collect water and analyze it once a month. We started in January 2020, and it was awesome because the conservation district was able to send their technician out to school, and he came to the classroom and taught all the kids and I how to do the sampling. I had done some other samples with Jeff as well, but he came to school and was able to show all the students and teach them. He took several days, and one day we went down to the river and collected the water, and then he showed them how to do all the titrations and everything. So that's some of those pictures there. And then this year, our school is going really towards the road of project-based learning. And so I am working on developing a project-based learning unit around Riverwatch for kind of the final project for my chemistry students. This year I only have 8 students in my chemistry class, so it's kind of been nice. It's just kind of a learn as we go and experiment and see what works in the classroom. And this is kind of what we've been doing these last few month or so, I guess. We've kind of been into this unit that I built. We started out with kind of having the students look at their relationship with water, and we talked about the Animas River and the Gold King mine spill and how it affected so many people, not just in Durango, but all the way down to the Navajo reservation and all of those things. And so then I had the kids kind of think about, like, why do you care? What's your relationship to the river? And so these are some of the little infographics that my students made about their relationship with water and how they use it. It was interesting to see. It's not just showering and drinking, but they fish and they use it after they play sports. And there was a lot of things that they came up with. And so that was really interesting. And that's kind of how we started looking at this. And then we looked at some water-related disasters, and each group of students looked at different things that impacted water quality in some way. So some students looked at red tide in the Gulf of Mexico. We looked at the Deepwater Horizon oil spill. Like I said, we looked at the Animas River and how that impacted things. And then we started kind of getting smaller and smaller. So we started a little bit of river ecology and talked about the stream continuum concept. We looked at river size and how if you get 2 one-size rivers together, you get a 2, and calculated kind of our stream size for the Mancos River at our site. And then we started delving really far into the Riverwatch parameters that we collect and analyze. And so we started kind of creating graphs of the data. Now that we've been sampling for a little over a year, we have enough data to kind of start seeing some trends. And so these are some of the graphs that the students have been working on the last week about different trends that they've seen at our site. And then yesterday, actually, we started looking at other sites on the Mancos River. So it's awesome because the Mancos Conservation District does 4 other sites and maybe more, but we looked at 4 other sites. And so we started comparing, we're going to start comparing what the data at our site looked like to the data at some of the other sites, and then tie it into that river continuum concept. So what are we seeing upstream? What are we seeing downstream? Our site's kind of right in the middle. So the students will look at that. And then their goal is to kind of create a report on the river. Ultimately, I'd like them to maybe present their reports to the town board or something like that. This year that won't happen because it's 2 weeks till the end of school. So we'll be pushing it to even get this done. But my goal ultimately is to bring in the community and have them kind of show, like, this is what we do with Riverwatch, and this is why it's important to us, and look at not just like the parameters, but this is why I care about these parameters and taking care of the water. So that's kind of, did I cover everything you wanted to hear about how I implement it in the classroom?
Yeah, I think so. That's great. I mean, it's so cool and important, you know, because at its core, Riverwatch really is simple, right? You know, you're measuring these things monthly, but to kind of provide some background and some depth to why you're doing it and the things you're doing is, I think it's great. It's really impressive, especially how soon you've done it. I guess I have a question is what kind of challenges, I guess COVID obviously provided challenges for everyone in a lot of different ways. What kind of challenges have you faced since you've introduced the program?
Um, well, I think COVID was a huge one.
Mhm.
Um, that's why I ended up with this little picture. It turned out kind of fun because I couldn't be with students, but I could still bring my girls on campus to collect water. So I did water analysis with my kids in my kitchen. And so they got to experience it too and came down and played in the river. And so that's that middle picture. But COVID's been really hard. And then I think one of the biggest challenges is just like the actual chemistry. um, and understanding like, chemistry is hard. Chemistry is challenging. And I think getting them to understand what's actually happening with the color changes and the cool titrations they're doing is a hard part, but we're getting better. So
That's great. Well, it seems like you guys are doing a good job. Did you guys have any questions for Sansa? I think you're muted, Megan.
Thank you. One of the things that we're developing right now, and Michaela and Barb have worked really hard on this, and Bradley is developing some additional online training platforms that maybe help to describe some of these in a little bit more depth, but maybe provide just another perspective. I'm guessing from my brief stint teaching Sensa that sometimes having that alternative perspective of describing something that you're physically working on is great. But the other important piece about having you present today is that we have teachers all over the state that I'm sure are have similar challenges and maybe opportunities for collaboration or things that have been done differently. But I just really love the partnership between the high school and the work that you guys do and the conservation district, and that you are comparing and contrasting that different data. It's really exciting to see that comparison. I love also that you started big picture, like talking about near and far disasters that have impacted water quality, from oil to metals and pH, to, I forget, from red tide. Yeah, just all these different aspects that impact it. So yeah, no specific questions for me, just gratitude and very impressed by kind of that whole scheme and the perspective that you've drawn from this.
thank you.
Well, and I'd like to add that, you know, since I kind of know the whole state and the program, that I don't think you maybe realize the unique role or opportunity you have there in Mancos, both of you two in your school. The fact that Mancos got involved in Riverwatch because they got funding through the Clean Water Act to basically they wanted money to deal with the mining issues in Mud Creek and the basin there and the ag issues. And that money came through the non-point source program at the health department. But that money required that they create a watershed plan or a watershed management plan. And so they needed to collect data and all that to do that, but they had the vision to bring in the schools, the high school and the middle schools, to fulfill both their mission as a district, but also to integrate bringing the schools into real management issues and planning and data and interpretation, and what do you do with that data to restore and protect those rivers. So you may not realize this, Sensa, and all your students, but many other schools would love that relationship with another entity that has a larger role in the watershed.
Mhm.
And likewise, many organizations are out there. They can't find a high school like you and a teacher like you and students like you have to work with to integrate, the joint missions and leverage the resources and the energy and the passion there. So I don't know if you realize it, but what you guys have is fairly unique. And, I did Riverwatch for 30 some years, and you guys have successfully kind of put this relationship together. And I'll say the district has worked on it for a long time. So it's really rewarding for me to see it come together. And I just keep it going, and we should brag on how unique it is, and that the goal should be that it's not unique, that you guys are actually boring.
I like that. I do. I love working with the conservation district, and I love having that relationship where they can come in and provide that outside input and stuff for the students is really important. And that's something we're really working towards in our district is working with the community. So I do appreciate it very much.
Yeah, that's great. So then I guess the next part of this would be Connor's presentation. I'm curious on maybe a little background, either of you, like how, because you think of, how would you introduce this topic, and how did you guys think of it? How did it come together?
Yeah, I think that's an excellent question. So Miss Wolcott but she wanted me to join science fair during the beginning of the school year. And I think for about 4 weeks, we were trying to figure out what I could research. And I almost dropped out of science fair because I just couldn't think of something. And then finally, she said, what if we did something about water and space? Because I was looking at something in space. I just didn't know what exactly. And we kind of just decided on, well, water is a very important resource in space, and it's something that we could utilize. And so we began to make up a plan on how to research water in space, and all the dots connected to Riverwatch as our testing materials. And so we just went from there. So I kind of did as background research. I wanted to know what water is used for. And there's a lot of stuff that it is used for. You can make hydrogen fuel. And I think that the major one that I was studying was, it's a resource for astronauts. Especially in this year with the new the rover landing on Mars, there's a new interest in space exploration. And so I was thinking, well, astronauts might be the next step, but they'll need lots of water to get from Earth to Mars, or even to the moon, or wherever they want to go. And so I just finally decided on the question of what is the water quality like on an asteroid? Is it something that we can drink? And is it kind of logistically speaking, is it something that we can actually get onto a ship and drink? So those are my questions for my project. And I kind of went from there. So the first thing that I had to figure out was the type of rocks I wanted to use. I don't have that much money to go out and buy rocks. And so I kind of had to use what I had. I wanted to use silicate materials because, the near Earth asteroids around Earth and Mars and the asteroid belt are made of those silicate materials. And then there's also some heavy materials, some materials that are also, the asteroids are also made up of. And so the funny thing is I found my rocks that are going to replicate asteroids in my backyard, which I think is super cool. Being able to do this experiment and getting the rocks for this cool experiment just from my backyard was awesome. So I was able to use Mancos shale, quartz, and mica. And actually for the metal, we dug into Miss Wolcott's closet back in her science room, and we found some iron pyrite. So, of course, it's not the top tier metal that would probably be, found on asteroids, but it's super close, and it's what we had. So I think that was pretty cool to see those resources and kind of test them. So what I did is, geologists, I was talking to a lot of geologists throughout my presenting in regionals and state. And the one thing that I found out was that surface area is a very major factor in water absorption. And the surface area and therefore the water absorption can affect the water quality of the rock, or of the water from that rock. So I had to figure out a way to make the surface area as close as possible. in a high school laboratory, it was kind of difficult. I mean, you think about it, you got mica, which is a really long piece, and then you have something like quartz, which is kind of a thicker piece. You have shale, which is kind of, flaky. And so it was really hard to get like, cubed on for each rock. So I kind of had to kind of guess it, make sure, estimate, I should say, was kind of measuring the surface area and trying to make sure that all of it lined up. And from there, I try to replicate asteroid conditions. Of course, there's a lot of factors that go into replicating outer space. And here at Mancos High School, I was able to use only dry ice to replicate somewhat of coldness. I mean, there's a lot of like, there's radiation from the sun and other parts of space, and there's like, the vacuum of space. And of course, it's a lot colder than just some dry ice. But I was able to put those rocks, put them into deionized water, so I had clean water, and I was able to freeze them for the weekend with dry ice. Just trying to replicate the space like conditions as much as possible. And after that, I took them out after the weekend and let them thaw in like their own atmosphere. I didn't want anything to evaporate. I wanted them to be in closed spaces so that nothing was able to be mixed in, so I had accurate results. And from there, I got the Riverwatch materials. And I think that was the real cool part of this experiment was, I never really experimented with like sulfuric acid and the EDTA, and just watching all those color changes, adding the buffer and the acid. I think it was a really cool experience, and it made me kind of more appreciate and just enthusiastic about learning science. And so it was really cool to see all this chemistry come together and get a real result, something that you can look at paper and know what's happening. And so I thought that was really cool, and it was just an awesome experience. And so I kind of forgot to go through my slides. Back here, these are the test tubes that I used. If you can see them, the beakers, not test tubes, beakers. I put my water quality in. And so I had lots of results. And so the one thing I found, the first thing is the iron pyrite. It was kind of hard because it mixed with the ammonia buffer. I think in order to either the alkalinity or the hardness measurement, you have to use an ammonia buffer. And it kind of messed with the iron and the iron pyrite. And so I wasn't able to get really good results. So I kind of scratched that. So I was going with the silicon materials. And a lot of these, because of the surface area, it wasn't exact measurements. And I think if I'm definitely going to do this project again, there's a lot of stuff I can improve. And one of them is that surface area. And so there's a lot of results that I could definitely improve upon. But what I found out and what my hypothesis was that silicate materials, including Mancos shale and mica, would absorb a lot and have a high water quality. And so what I found out was that is true. And Mancos shale and had a really high, not a high hardness and alkalinity, but it was moderate, almost to the soft side. And if I actually go back in some slides, I have, that's too much. Right here, I have a little table, and this is what I was comparing my results to for acceptable water quality. And so what I did is I took those results, compared them to what is acceptable, and kind of saw what rock had the most potable drinking water. And so it's kind of interesting to see that, I could use, or I can measure the rock or the water from my rocks and see how it relates to water quality testing in cities. And so what I was able to find was that silicon, oh gosh, that's technical difficulty, thank you. What I was able to find was that the silicon materials, specifically shale, were able to provide soft water, and they had a relatively low alkaline content. And so what I was able to, also really cool thing in this presentation, is I was able to understand what alkalinity was and hardness. It was kind of something that was really confusing at the beginning, but I was able to understand how alkalinity is the amount, how the solution resists pH changes. And then hardness is measuring, not heavy metals, but you have your calcium and some of those metals in the water, and it's measuring that. And so I was able to, it was really cool to see, kind of learn about that. And understand that my hypothesis and see that my hypothesis was in fact correct, because they're called C-type asteroids, and those are just asteroids that are made of silicate materials, would have a high potable drinking water content and high absorption rate. And so what that means is, like, if NASA or some space company or space administration was trying to go and get water for either potable drinking water for astronauts, or even obtaining water to create hydrogen fuel, they could use silicate asteroids, C-type asteroids, to extract as much water as possible for the most potable drinking water. And I thought that was really interesting, and it was a really cool experience. And like I said, I think my favorite part was definitely using the Riverwatch materials and just looking at those color changes and seeing how everything fit together. So hopefully my rambling made sense. And if you have any questions.
So awesome. First off, I didn't know very much about asteroids. I'll be totally honest. They were like C-type asteroids. So even, you know, I generally think about Riverwatch on this planet, and you've really like blown it out of Earth's orbit, which is really fun. So yeah, you talked a little bit about things that you might do differently, and I really like that idea of surface area being really critical to that. Are there other things that you might do if you were to repeat this experiment? And if you could also tell us about like the mass or something of your rock material versus the amount of water that you use. I'd be curious about that, because obviously you needed enough to do all your different analytical experiments from, but yeah, what did that look like?
Yeah, definitely. So I'll tackle the what I'll change next time. So for surface area, I was talking to a geologist from the Colorado Association of Geologists. And what they were talking about was, well, if I pulverize all these rocks and I put them through sieves, or sieves, I don't know how to pronounce that, sorry.
I heard both ways, you're good.
Okay, yeah. If you put them through those sieves, they'll all have almost the same amount of surface area. So even pulverizing them into dust, that will allow them to have the same surface area, and it'll be just a better way to get an accurate measurement. And so that's something I'll do. Also, just maybe even getting other rocks to test on. I would definitely like to test on other metals, because my iron pyrite didn't really work out so well. And then just even other silicon materials that I could find and see what water quality is on those rocks. And so what was your other question? I'm sorry.
Volume to mass, like how much total? What was that ratio?
I don't know if it's on here. It probably isn't. It's in my result log, I'm guessing. I did definitely weigh all the rocks, and that was mainly for the absorption rate test. So I had two different tests. I had a water absorption test, and I had a water quality test. So the water quality test checked for the water quality, of course, using those Riverwatch materials. And then the water absorption rate, I used, what I did is I heated the rocks to get all the water out of there. I weighed them, and then I was able to soak them in water as much. I filled up as much water as it took to get the water over the rock. So the rock was fully submerged. And then I just let it set over the weekend to see how much the rock would absorb. And the one thing that I learned from all of my interviews was that what I should be testing for is not absorption, but is it polarity or not polarity? I forgot the term, but it's the amount of kind of holes and porosity. That's what it is. Thank you. This is why I misspoke. The porosity of the rock. And so being able to know the difference between porosity and absorption is a really cool thing, and something I didn't know about. And so looking at those rocks and seeing, definitely like mica and shale have more porosity because there's little holes in the rock and the water can fit in there. Unlike quartz, where the porosity is probably very low because it's more of a solid material. And so kind of knowing that not only does volume and mass affect the rock, but also how that rock is, how the chemical structure of that rock is made up, and how it can hold enough water. So I would definitely kind of do more research into the porosity of all the rocks and see how that differs.
Good idea. I definitely remember like granular activated carbon, like charcoal, basically. 1 gram of that, right? Like think centimeter by centimeter roughly, has the surface area of like a football field.
Which is cool.
It's so
awesome.
cool. Yeah. So anyway, great responses. I have more, but I'll let other people go first.
Maybe. Yeah.
That's just really good. I was really impressed with that.
Yeah, congrats. That was awesome. I think you might have skipped over a couple slides. I was wondering if you could just scroll through from the beginning.
Yeah.
And just quickly show all of the slides.
Okay. Yeah, that was my bad. I kind of got into the presentation and not the actual slide.
That's okay.
Yeah. So I have my introduction, kind of why I wanted to do this. Background information. This is talking about what alkalinity is, hardness is, and pH, and kind of figuring out why I'm testing these. And then there's my table on what I'm comparing with my results. Then I have my methods. And so, of course, I have longer methods for both of my tests, but they were like 2-3 pages long. So I didn't want to fit all of it in. So this is the summed up version of the methods for water quality test and also the absorption test. And then, of course, I had my control group, my controlled variables, and the uncontrollable variables. And so, of course, my control group, I wanted deionized water so that the quality of the water was the same at the start. Controlled variables, as much as possible, the surface area of the rock, of course, type of water, which was deionized, the general temperature, which I used the dry ice, and the time exposed to the conditions and the amount of water. So well, this varied. So for water absorption, I use as much water needed for the rock to be fully submerged. But for water quality test, I used 125 milliliters just because I didn't want, a one solution to be more dilute than the other. So that's why I had a constant 125 milliliters for the quality test. Uncontrollable variables, I talked about, cosmic radiation and all that. There's also specific or the mass of the rock, because that changes varying on the rock, and so which is what I'm testing for. So it's kind of cool to see the difference in the mass of the rock and the polarity. And the variables that I didn't test for, of course, were cosmic radiation and the presence of heavy metals. And so even though I tested hardness, there was you can also test for other heavy metals. And what I needed to do is go over to Durango, which is just over our neighbor, and I could have had my water tested at their testing facility. I just didn't have time. I ran out of time, but that would be something I would do next year. Definitely test for the presence of those heavy metals. So then again, here's my results, and went over that.
Hunter, we can help you test some of those too if you need.
Okay, awesome.
Leave it on.
Okay.
Leave it on this slide for a second,
Definitely.
please.
Because when I was talking to, it was a mining association for my special awards at state. I forgot where, but they were very hard on me, which is really good. They were able to analyze all my data and stuff, and they did find not lots, but a little errors. One of them being I shouldn't have used absorption rate. I should have used polarity. But I think it's really good to have that strong critique, because I learned a lot, and I'm going to make sure to get even more accurate results next year.
How come there's no results for iron pyrite again? I missed that for alkaline hardness.
Yeah, because when I was testing, I believe it was either hardness or alkalinity. It reacted really weird with the ammonia buffer. It basically, the color change just didn't, it had a weird color. And so I think it turned black for some reason. And so I just didn't want to guess any results. And so I kind of scratched it.
Really, really good. You're a good scientist. That the titration actually iron interferes with the chemicals in that test.
Okay.
For it to do its results. So that's why it didn't work.
Huh. Okay, cool. Is there, just speaking to, because you definitely know a lot more than me, is there a experiment or a test that I could use that to test those iron materials?
What you could try, and iron pyrite may be so high in iron it might work, but we do have a powder that looks a lot like EBT powder. It's called calmagite, and
Okay.
it's supposed to work with that interference and create the same relative color changes that the EBT powder does. So you could try that.
Cool. Awesome.
Another interesting, I mean, if you could do metals results and just, even if you could only do a few of them, you would see that iron obviously is going to be really high in iron than the other rocks you're performing yeah, anyway. And then over here on your deionized water is a lot like acid rain. You know, the acidity of rain and snow is usually below a pH of 6. It's in the 5s. In theory, you don't have any alkalinity
Okay.
below a pH of 4.5. So I'm looking at what you got there, and you had no phenolphthalein and very, very little total alkalinity. And, you know, that's like testing the alkalinity of Cement Creek. Up by Silverton, which is a pH usually of 3.3 or 4.5. So that's good to see. You know, and in theory, deionized water has no ions in it. It's super, super pure. So you shouldn't get any hardness either. So good to know that our deionized water is performing as it should.
Awesome. Cool.
And since if you send me a little reminder, Bradley and I, we can send you out a little bit of that calmagite stuff to test with.
Awesome.
That works better.
Cool. Thank you.
That'd be cool. Thanks. All right. Are we good on the results page?
Yeah, thank you. Thank you.
Okay. Awesome. So then I had my other results, and this is in graph form. And so I just kind of looking at both, you know, absorption, water quality, and the pH and temperature. And one thing that was really cool is that Ms. Wolcott had both a pH reader with the temperature, which honestly, I never understood that pH and temperature correlate so close together. And so it was really cool to learn that and use it in my experiment. And then, yeah, on those graphs. And then for my notes there, the hardness for mica was pretty high. And so I just couldn't put it into that small graph. And so I just had to put that out there. And then on my discussion, I was just talking about kind of how my project went, you know, that there had almost no cross contamination because of the procedures I had. And then just kind of theorizing that it was a C-type asteroid because of the results that I saw. And just this discussion here is really close to the conclusion. Just kind of discussion was just talking more about what I saw from the results. And then the conclusion was just kind of what this meant for the future of testing water quality up in space, which is really cool.